This is the third video on matter, measurements, and math. And we're going to finish up our discussion of measurements and the things that have to be considered. So I thought I'd pull my balance out and kind of remember the place value. We're going to look at that, but remember the significant figures to a measurement. We never really talk about a measurement, or we don't really talk about significant figures unless we're talking about a measurement. But if I put my penny down on the balance here, it's 2.47, and now I can maybe change to 48, but we would say there's three significant figures, there it goes, to this measurement. Now if it happened to be 2.00, that's just coincidence. It's still three significant figures. We don't consider zeros that are leading, that's on the left, but we do consider anything that would be to the right. We've talked about, I guess, significant figures in the last video. Let's transition to things like place value, scientific notation, units. This is what we need to focus on with this video. So the place value, analytical balances that are very, very precise, not like the one I showed that stopped here, but those that are very, very precise can go two more, I guess, digits to the right past the decimal point. We call that the 10,000ths place. For place balance, you might hear it said that way, or it's a thousandths sensitivity balance. It's talking about this side of the numbers past the decimal point. So two place balance would be what we just had. It's less than $200-300, but these would probably be more $2,000-3,000, these types of balances. This can be read to the 10,000ths place, or fourth place past the decimal point. So this number here, when we talk about place value, does not have a decimal point. So we'd really not consider that necessarily a measurement, necessarily. We are going to focus on those measurements that have decimal points, but we can still imply a decimal point is right there. So if it's not there, just write it in. All numbers have, I guess, place values, whether there's a decimal point or not, but only measurements, in our case, have decimal points. So let's look at this place to the left. If you're left of the decimal point, you're at these particular positions. The ones, that's where the 8 is, the tens, the hundreds, and the thousandths. Now to the right, I guess you're kind of going to the south side, to the like saith, so you're going not to the oneths place, but tenths place. And the way you can think of 0.4 as being in the tenths place is that 0.4 is kind of equal to 4 over 10. So that's why we call that the tenths place. This would be the hundredth place, and this would be the thousandth place, trying to like Elmer Fudd or something like that. The TH being very pronounced. All right, so that's place value, just knowing that it's ones, tens, hundreds, and then to the right it's tenths, hundredths, thousandths. That's place value. Oh, and this was not a measurement because it doesn't have a unit. As we finish up discussion of measurement, they're going to have two things, decimal point and units. It should have a unit on it if it's going to be a measurement. So the units, what kind of units can we have? Well, we can have, I guess, SI units, or Systems International, or we can have the, I guess, English or American system of pounds, and then I guess volume can be in pints. But we're typically going to have literature that talks about kilograms, grams, and as far as volume, it's going to be mils and liters. So these would be the systems, units we're going to look at as grams would be for weight, and liters would be for volume, or milliliters. We can always convert, I guess, liters to milliliters to kiloliters. It's kind of an easy standard conversion. Kilo is always 1,000, so we can actually just say, if we don't know what kilo is going to do to the number out front, we can just say, well, that's going to be 1,000 times it. So 61.2 times 1,000 grams. You can just replace that with 1,000. This times 1,000 grams. Now for milli, we actually divide by 1,000, so it would be 1/1000th. But we'll do more of those calculations as we go. Weight is not a mass. Just want to remind you that we can measure, I guess, weight on Earth, but mass is different. It's the, I guess, the mass of a Object does not change based on gravity. Of course, we use weight to assess mass, but they're not exactly the same. All right. So we said kilogram just means 1,000 grams, so you can replace the kilo with 1,000. And we can say if we want to go from grams to milligrams, we can times that by 1,000 and go from grams, which is a bigger unit, to milligrams, which is a very, very small unit. So that's why we have to go up in terms of the number, because this, you can put 1,000 of them into the gram, and of course the kilogram is much, much bigger. We can put 1,000 of these. So it's a unit thing. If the unit that you're considering is getting smaller, then the number has to get bigger. So a kilogram, just know, has a unit that's much, much larger than the gram unit. And the gram unit is 1,000 times larger than the milligram unit. I'm not going to ask that you memorize certain conversions. I do kind of want you to remember the Systems International is grams. The Systems International is volume, is liters. Those are some big ones. We'll often convert between Celsius and Kelvin, so it's not that there's one or another that's better. Designate the units as measuring weight, volume, or length. So let's go quickly on this. This would be a weight thing. Mass being measured, kilograms. The person is 2 meters tall. That would be certainly a length. The medication contains 0.50 grams, 2 sig figs there. That would be a weight or a mass, and the bottle contains 1.5 liters of water. That would be a volume. Scientific notation. We had said in class that you use this when you have something very, very, very large or something very, very, very small. So it comes up in chemistry as the number of atoms can be very, very large, or we can have a mass of some electron, let's say, that's very, very small. Scientific notation helps us deal with those kinds of numbers. So a coefficient, a number with a decimal point, I guess we're going to have a power of 10 that we're often going to be considering for large or small numbers, and the exponent is going to be negative if the number is very small, and it's going to be positive if the number is very, very large. So let's look at this number. Is that a large number or a small number? And the thing to consider is that it's a negative, 10 to the negative 10. That means it's a small number. If it was 1.2 times 10 to the 10th, then that would be the opposite. It would be a very, very big number. So the rules for going from standard notation to scientific notation is this. If there's a decimal point, of course, start there. If it's implied, write it in, because we're about to move to make this, I guess, a number in standard to a number in scientific notation. We move it 1, 2, 3 spots to the left. So that's a large number, 5,983, becomes 5.983 times 10 to the third. I do want to point out that this is not a measurement, so we do not see a decimal point there. So we're not going to talk about sig figs. This one would be something we could address significant figures in, and if you ever see a measurement with decimal point, do not add or take away any significant figures as you go from standard to scientific notation or the other way. So we see it, we maintain that. This is 0.00034, there's only 2 sig figs. If we move the decimal point to the right for this small number, we had to move it over 4 spots going to the right, so it's negative 4. If you're going down, you're going to go negative, and this is still 2 sig figs. So either way, in the scientific notation or in standard notation, we have not changed the number of significant figures in that measurement. Of course, this kind of breaks down when you have really, really large numbers. This is probably not a measurement because you can't be as precise as you would like to be, but I tried to determine in a grain of salt how much sodium ions you have. So let me see, just the total number of atoms, whether it be Na or the Cl, just add them up in the crystal that you have in a salt shaker in your kitchen. Turns out, estimated, that we have 2.4 times 10 to the 36 ions or atoms in sodium chloride crystal. That's a lot. I mean, you got to think this is a billion right here, would be the billions mark. So we have kind of billions upon billions upon billions of atoms within just one little salt crystal. That's big, but we can also look at very, very small things like the weight of an electron in grams. That's approximately 9.109. I have a lot of sig figs here. 9.1093897 times 10 to the minus 28 grams. So if we did that, if we converted that to standard, of course it'd be a very, very small number. And it's one that's not necessarily measured directly. It's one that can be calculated. All right, we're almost done. We're just going to look at some sample problems and apply what we've learned regarding significant figures, units, place value, scientific notation, all of that kind of coming together. Convert this number to standard or scientific notation. So it's in standard. We're going to convert it to scientific notation. Now I'm going to do something different than what maybe you might expect. 1, 2, 3, 4, 5, and I'm going to stop right there at the 5 and write 0.8 times 10. How many spots did I move? 1, 2, 3, 4, 5 times 10 to the minus 5 because I went with a small number. I had to go to the right. This better be small. Now, of course, I don't have a unit on this, so we're not sure what they're measuring. But I didn't want to go here because if I did, I'd have to write 8 You can't use a decimal point unless you have a 0 on the other side. But as soon as I do that, then I would have 2 sig figs. I would have 2 of those, whereas here I only have 1. This is the only significant figure. So I can keep that, maintain that by using this particular form of the scientific notation, stopping short of the other side of 8. 2, 3, 4, 5, yeah. So this is not a measurement, implied decimal point there. We're going to say 7.2 times 10 to the 4th because we go 1, 2, 3, 4 spots to the left. 2.0 times 10 to the negative 2, kind of going backwards. Need to make sure I got this right. So we'd go 1, 2, and that would be 0.02. And since we are keeping that sig fig, it would be 0.020. And 1.8 times 10 to the 5th. This one's going to be a little bit harder to keep sig figs because I'm going to have to add a lot of zeros behind. So we're really not going to consider that for this case here. We're not going to keep the same sig figs. We just can't. So I'm just going to put those 4 zeros I would have. And to make sure I get them right, 1, 2, 3, 4, 5. Yeah. So I put them back, and we'll say it's 180,000, and maybe just get rid of the decimal point. It's just hard when you have a scientific notation of a large number and you're trying to keep the same sig figs in standard form. It's just kind of hard to do that. All right. If you move the decimal point to the right, the power is negative. If you move it to the left, it's positive. So what are the number of significant figures in this one? 2, 4, 6. There's 6 sig figs. This one would have just 4 sig figs because the leading zeros are not significant. All of these having decimal points. Don't have our units, but we'll go with this. This would be 5. And this one would be all of them, all 7 of these digits because there's no leading zeros. What are the numbers below in terms of scientific notation? Let's just convert that. 1.001 times 10 to the 3rd. 5, I don't know why you would do this for 53, but 5.3 times 10 to the 1. Now certainly this one's going to be a little bit harder. We're going to move. We don't have a decimal point. All of these have not been measurements, but 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'd say 6.9263 times 10 to the 9th for this one. Minus 392, we could say minus 0.392 times 10 to the 2. Don't think it's negative, it's just a negative number. And then last, I'll put it down here, 3.61 times 10, moving it 1, 2, 3, 10 to the minus 3rd. We're moving it to the right. Small number better be negative. All right, I think we're good on, sig figs, scientific notation. Please make sure you practice those problems that are going to be posted. The quizzes.com website that you can use. Make sure you make use of that. I just added some notes regarding how to work the calculator, but I think we're going to skip that. Thanks. Bye-bye.